Hello friends, MoNaCo here. We're about to start our sixth notes video on periodicity. There is a typo on the first page here. If you can find it, you let me know. There's a little Easter egg in for it. We're going to understand what it's meant by the team term periodicity and how it is used in the periodic table. So if you look it up on the web, its periodicity is the quality or character of being periodic, the tendency to recur at intervals. This is the most important part, the tendency to recur, which means to happen again at intervals. Okay? So the whole point of this lesson is to recognize what periodicity is. We use this idea daily, weekly, and yearly as it applies to time. So we know that an hour goes from 0 minutes up to 60, and then it starts over again. A day starts at 12:01 a.m. and then goes all the way to 11:59 p.m. and then it starts over again. A week starts on Monday, ends on Sunday, starts on Monday again. It's repeating. A year starts on the 1st of January and ends on the 31st of December. So periodicity is how things happen in cycles. You know, sun comes up, sun goes down. Moon comes up, moon goes down. Periodicity is that term. We're going to explore how it applies to chemistry in the periodic table, because guess what? The periodic table is arranged in a way that's supposed to show you some cycles. You got to understand what those are, though. So here we are. Why this table is periodic. As you move across a period, which is the rows, horizontal, okay, that's the horizontal row, we have a situation where our nuclear charge increases. Why? Because every time you make a step towards the right, you're adding another proton to the nucleus, and protons are positive. There's the additional proton. It wins a tug of war with an additional electron. So stronger the protons are, they pull on those electrons. Pull it more tightly. As a result, there's shielding that happens. Shielding does not increase. Kernel electrons interfere with the attraction between the protons in the nucleus and the valence electrons. If you're having trouble recognizing this, here's a little Bohr model. There's the nucleus that has a positive charge. Then you've got these rings of electrons with negative charges, okay? You know, little negatives there. As you add more protons, this outside ring gets pulled in closer. Okay, because the protons attract the electrons and it kind of sucks everything in together. We call these electrons in the middle the kernel electrons in these orbitals, and they're kind of running interference. The more of them that there are, the more the nucleus is shielded from the valence shell. So the valence is out here, and the nucleus is in there. So the more rings of electrons you have, the more shielding that is going on. Shielding does not increase as you add more protons and electrons to a single shell. It only increases when you add another shell on the outside. So if I added another ring of electrons out here, then there's another row or orbit of electrons in there putting more shielding into play. Okay, so the protons and the valence electrons don't feel each other so well. Every element in the same period row has the same number of kernel electrons. So the whole shielding game is a game played between the nucleus and the valence ring. Okay? There it is. The non-shielding outer shell and the shielding inner shells. The non-shielding outer shell and the nucleus are kind of like this tug-of-war situation. Okay? And the way you can kind of look at it is you look at the inner shell electrons, you take them away from the actual nuclear charge, and you get a kind of a number to see what the shielding value might be. We don't really have to do that on the regions, but we have to know that periodicity is due to shielding. As you move down a group, we have a scenario where the nuclear charge increases, but shielding also increases because, as I said, as you move it down a group, oopsies, let's get that smartboard working here. The nucleus, as you go to the next group down, you're adding another ring of electrons. And since the whole shielding game is a game of tug-of-war pulled between the nucleus and the valence shell, the more shells of electrons that are in the way, the more shielding that we have. Okay? So additional orbital energy means more kernel electrons to interfere with that attraction between the protons in the nucleus, positive charge, and the valence electrons out in the orbital that's furthest away from the nucleus. If shielding increases, that trumps everything. So as you go down, shielding increases. Okay? As you go down a group, shielding increases. But as you go across a period, shielding decreases. Okay? That is kind of the takeaway here. This electron shielding happens. It causes periodicity of the properties of the elements. So you should be able to recognize that there's more patterns within the periodic table here now. These patterns give us information when comparing one element to another. So if you're asked, okay, which element has more shielding? This element or this element, you'll say, oh, it's this one. Or which element has more shielding? This element or this one? You'll say, ah, it's this one. Okay? So that's another little pattern that's going on here. There's some practice packs, page 15 to 22, 27 and 28 should be useful here. After this video, we're going to get into more of those trends. So you're going to have to pay a little bit more attention to what's going on. And again, I mentioned the Easter egg is a typo on the first page. So mention what that is, and you got yourself a little stemmaroo. See ya.